All right. So I think maybe the main thing that we wanted to focus on was there was a fact that we used in class. Let's see if I can find it. Okay. So in class, I made this claim, right, that one can write beta in terms of this. Okay, so let me quickly remind you what we're doing. So okay, so we have a vector beta. Okay, so what are we given? We're given some vector beta, okay, and we're given these row vectors alpha 1 to alpha m, and we know that one can express one can find the row reduced echelon matrix, right? So this is capital R, this is capital A. So, and this is the invertible matrix P that maps capital A to capital R, right? Wait, what? What have I written? I forgot the equality. Okay, so then because this is in the row reduced form, I've just sort of written the row reduced form more explicitly. Okay, so we're basically writing R equals P, right? Okay, and in class we sort of asserted that beta can be written as B k sub I rho I, okay, where rho are the rows of this row reduced echelon matrix. And why that was because we had already argued in the previous class that, and this basically came from how we were doing the proof of theorem 11, that, you know, suppose beta is some, because obviously beta belongs to the subspace W, right? So there would exist some coefficient C's such that when you multiply them with the row vectors, you would get the vector beta. And basically all that this is doing is it's just expanding this and writing out the rows explicitly in terms of capital R. And then when you write it explicitly in terms of these capital R's, right, we know that these things have a special form, right? Because these are the row reduced echelon matrix. So one can use the properties of this, the fact that it's a row reduced echelon matrix, and conclude that this is the main thing that we want to conclude, right? That I've written over here, that Bk sub j is Cj. Okay, so these coefficients that we were trying to find, they're basically determined in terms of the bkj entries, and kj, remember, was just the I think I had written it somewhere. Where is it? Yeah, okay. So ki is the index of the first column for which row I has a non-zero entry, right? So this is the definition we were using. Okay, so so this is sort of the nice problem statement, that you're given beta as B1 to Bn, and you're trying to see whether beta belongs to W. And so in one of those steps we were trying to check whether what the coefficients should be, right? If one were to write beta in terms of coefficients of in terms of a linear combination of rho I. Okay, so this is basically the step. Now the question is, how do we write? So how does one write? Let me see if I have it written somewhere. So now what we wanted to know was, how do you write beta in terms of linear combinations of alphas? If it's a given beta, you can write it as linear combinations of rows. That is fine. Okay, so here, what are the question was, so this is part B, what are the coefficients? So you want to write beta as a linear combination of xi alpha I, and we're asking what these xi's are, right? So to compute these xi's, what we're going to do is, we already know that beta has this form, right? And we also know from this matrix here, right, that's R equals PA condition, one can write rho I as this matrix P multiplied with, basically linear combinations of alpha j's, right? Okay, and now what we're going to do is we're basically just going to do a very simple substitution. So beta can be written as B sub ki rho I, this I already explained. And then you just substitute for rho I using this equation above. Okay, so this is step 2. So you make that substitution, and what you'll get is some coefficient times alpha j, and then this coefficient you can directly read off. Okay, so this xj will just be this part, and this is how you get xj in terms of the coefficients of the matrix, the coefficients of the vector that we are guaranteed belongs to W, and this matrix P that relates A to capital R. This relates A to capital R. Okay, so P times A is capital R. That is what we're using. Okay, so this combination sort of tells you what we wanted to do. So that was the so we worked out an example, and in class we basically used this fact here. Okay, and so I told you what the proof is. So this part is fine. Okay, and the second method is doing what? The second method is basically going to do the following. Now we are again going to consider the question of whether beta belongs to the space W, or whether there is some linear combination of alpha i's that matches beta. And the way we are going to do it is we are going to ask the question in the following form. So we're going to ask, does this system of equations have any solution for some betas? So what is this system of equations? So let's look at it a bit more carefully. So what this is saying is that, so suppose we write this is the vector beta, right? So we were writing each component. So what this equation is really saying is that it's basically just a component wise statement of the following statement, that xi, you take linear combinations with alpha i's and you want them to match beta. Okay, so you're writing alpha i's as this matrix. Okay, and now instead of writing the matrix alpha ij like this, right, because the multiplication looks more like like you're doing a left multiplication instead of right, because we are used to doing these kinds of multiplications. So what we're going to do is, instead of writing this vector alpha, we're going to write in terms of A, we're going to write it in terms of B, where B is basically just the column. So it's going to have alphas as column vectors. Okay, and then bx equals y. So we're going to ask for, is there any x, right? So basically it's these coefficients. So it's x1 to xn. So are there any coefficients x such that bx equals y, where y would basically be b1 to bn? Okay, and we already saw how to solve this, right? So we saw in chapter 1 that there are some constraints on y once you write b in like some row reduced form, and then using this one can determine whether for a given y there would exist some solution to this equation. Okay, and that is the same as asking whether for a given beta one can express it in terms of a linear combination of alpha i's, right? So that is sort of the main point. Okay, so now let's quickly do the example that we did, but now this time in terms of using this example. So let's quickly recall. So what were the two things we wanted to check? So we wanted to check, part A was that we wanted to prove that these vectors are linearly independent. So that would just be the same, right? You write the row reduced matrix and you check the ranks. That part is fine. The second part is the more interesting one. We want to know whether this vector beta, for some arbitrary b1 to bk, b4, whether it belongs to W, and if it does, can we write the coefficients in terms of alpha rates? It's basically asking, can you find xi such that beta equals xi alpha, right? Okay, so let's see how to solve this. Now we're going to use the same procedure that we described. So we're going to first write the matrix B, which is just a bunch of column vectors. So we write alpha 1, alpha 2, alpha 3 as column vectors. So remember, these are the alphas, so we put them as column vectors as shown. And now we're asking for which y's does the following system have a solution. Okay, so how do we do this? So recall from chapter 1, the procedure was as follows. So you write down the matrix, the augmented matrix, right? So let me remove all of this. We write down the augmented matrix here, and then we are going to remove all the entries over here by subtracting them. So we're going to subtract 2 times y1 from here, 2 times y1, 2 times y1, and then minus y1, right, to get this matrix. And then proceeding similarly, you can subtract the other things so that in the end you have the row reduced form, right? So you have 1 and all zeros, 1 and all zeros, 1 and all zeros, and you applied the corresponding operations to get some condition on y. Now remember that for this to have a solution, right, we argued that ax, okay, so we'll have ax equals y, right? So now, yeah, let's call it, let's just say a prime x equals y prime, right? So yeah, maybe you can also call it right. So this will have solutions if and only if ax equals y has solutions, right? This was like one of the theorems. So now what are we doing? Well, we are checking, okay, so if a prime x equals y prime, then so basically if you look at the condition arising from the third the last row, then you would have since all the elements of the last row are 0, you'll have 0 must equal to this last entry in y prime, which is y3 minus y2. Okay, and this gives you what constraint? It gives you that y3 has to be the same as 2y1, right? So it's written right here. And remember, we were checking beta was basically playing the role of y, right? So if beta was y1, y2, y3, y4, then this condition is basically saying that b3 has to be 2b2. And this is exactly the condition that we also found using the other method, right? Where we had bki was written as some combination of, bi was written as some combination of bki, bkj, something. Okay, I forget what the exact condition was. Let's see. Yeah, so bj was sum over bki rij, right? So you just multiply it, right? So this is the condition, and from this, if you remember, I guess maybe we have if you look at example 21 here, we had, when we worked it out, we got here it is, right? So we got b3 equals 2b1. Okay, and this is exactly the same condition that we got also by doing this other method. Okay, so if beta is in fact in W, then one can compute these coordinates x1, x2, x3, right, which are just exactly these coordinates. And how we do this is, you basically just multiply this guy, equate it. So you'll have, when you do the first multiplication, you'll have x1 equals this first object, and then x2 equals the next, and so on, right? So this will, x3, right, because it's 0, 0, 1, so it'll pick x3 equals the second row, and so on. Okay, and this will give you the coordinates x that you need that would satisfy. So sum over xi alpha I would then give you right, because the solution that you found here will also be a solution. So you found it in terms of a prime and y prime, but this will also be a solution for ax equals y, and a, remember, was just a bunch of alpha 1, alpha 2, right, like that, times x, the one that you found, has to be equal to d1 to whatever. So if you plug this in, this would give you this would give you the vector beta, right? So this is just saying beta would be a sum over xi alpha I. Okay, so this is exactly the same xi that you wanted. Okay, so that's basically all, and the other two parts apparently are essentially the same as what we did in the previous step, because I guess once you have a procedure for determining for an arbitrary vector what the coefficients are in terms of x, in terms of xi, then one can just unplug these different vectors. So do this procedure 3 times. For you treat beta as alpha 1 prime, alpha 2 prime, alpha 3 prime. You will get different x's, and then you can show a relation between those x's by writing down the transformation. Okay, so that's about it.